Good morning. My name is Ivan Pandev, and welcome to the second devlog entry for HyperMu. HyperMu is an original vehicle dynamics simulator using multi-body physics written in Python. Intuitively speaking, HyperMu is a virtual shaker rig, but with expanded functionality, namely being able to replay recorded lateral and longitudinal acceleration telemetry through a vehicle model center of mass. For this reason, I sometimes think of it as a 7 plus 2 post-shaker rig. It predicts values which are crucial to vehicle handling but are impossible to directly measure in race conditions. In the last video, I mentioned how frequency analysis could be used to tune out undesirable resonances and that some features for this were in progress. In a lateral acceleration frequency sweep, it was clear that our vehicle model had natural frequencies probably between 1 to 1.5 hertz by visually looking at it in the roll mode, which resulted in excessive tire load variations. In this follow-up video, we'll explore how to actually quantify these predicted harmonics and predicted load variations in HyperMu and see if we can improve the vehicle model's response. We'll use the vehicle model from the last video as a control, but I also created a modified model with roughly a 30% increase in overall damping rates as a first attempt to improve the harmonic response. Remember, we also noted in the last video that the dampers were entering their high speed domains in a telemetry run, so I significantly bumped up the knee speed as well. We'll create a HyperMu vehicle instance for each of these vehicle parameterizations in our Python terminal, making sure to read and accept the disclaimer that we saw at the beginning of the video. And now we'll compare these models across a handful of test scenarios to get an overall picture of how the vehicle model responded to the damper change. We'll call the tire response detail comparison function of the first instance, and we need to specify an other to compare to. In this case, the model that the model with the updated damper rates. The first scenario that I want to test is what we covered in the last video, a lateral g-force frequency sweep. So we'll specify that as well in the command, and we'll go ahead and launch that simulation. Okay, and this is the crux of what I wanted to share in this video. HyperMu's new histogram and frequency plots for tire load during a given scenario. Minimizing tire load variation is a key objective for predictable vehicle handling and maintaining high grip. So there are two ways to quantify it here. In this video, the control vehicle model, the self, will always be in orange, and the other, which is the vehicle model with the revised damper rates, will always be in blue. First, the histogram and the standard deviation metric will help us identify peak loads, minimum loads, and the spread of the data expresses the standard deviation, which generally we want to minimize. To the right is the frequency space plots, where we can identify harmonic peaks and potentially tune them out to minimize the root mean square, the length normalized area under the amplitude curve. Intuitively, the RMS represents the amount of oscillation and vibration in the tire load signal. Again, the goal is generally to minimize that metric. We can see that the increase in damping rates for this specific vehicle model and test scenario resulted in fewer unloaded moments for the tires and lower peak loads. Note the logarithmic y-axis, so this is a notable improvement we're seeing here. And moving to the frequency space plots, we did significantly reduce the harmonic peaks, including those around the 1 to 1.5 hertz domain, which are the harmonics that we identified in the last video. So it's exciting to see them here, and it's exciting to see that they have been attenuated, but it is at the expense of amplifying some higher frequency harmonics as well. So the RMS, our key metric, is lower overall with the higher damping rates. So we have an improvement for this model scenario combo. You might be thinking that the stiffer dampers would be a regression in scenarios including curbs and bumps, even though it's an improvement here. So we have a test scenario for that as well. A new unit test in HyperMu is simply called curbs, where the two right-hand side tires go over a sequence of bumps. So we'll specify that unit test and launch that simulation. The results here for the curbs scenario show us that while the damping combination isn't an overall regression, we are starting to see diminishing returns for stiffer dampers, especially on the right front wheel, um, being indicated by the nearly identical RMS and the nearly identical standard deviation in the histograms. So we likely won't benefit too much from further increasing the damper rates, uh, at least for this scenario. Finally, let's do a test scenario of real-world g-forces rather than synthetic unit tests. We'll go back to the compare tire response detail function, and as we did in the last video, we will specify um, the file containing our telemetry data, and we'll go ahead and launch that study. Okay. We see here that for real-world G profiles and a non-flat racing surface, which is an appropriate assumption for autocross racing, that's where this telemetry was gathered. There's no curb berms. The damper rates don't actually affect the tire model's load variation all that much. One cool thing to note is that the damper changes do seem to, once again, attenuate the predicted resonances around 1 to 1.5 hertz, um, which I'll highlight right here. Um, but the fact that the RMS isn't significantly lower tells us that other frequencies are being amplified to a roughly equal measure. There's technically an improvement, but overall, these metrics are not that sensitive to damper changes on smooth surfaces. So let's try one more test to get a more complete picture of how these damper changes affect the vehicle model on recorded telemetry. I'll specify a different comparison function this time, one that compares the lateral load transfer properties, but still creates histograms and frequency response plots. Same telemetry, we're running through it, and we're launching that study now. And there we have it. So lateral load transfer is related to tire load variation, but it's better suited to describing the vehicle model's cornering balance. Minimizing the lateral load transfer on a given axle maximizes the available friction at that axle, and the balance between the front and rear axles' lateral load transfer is a key contributor to the chassis' overall oversteer or understeer balance. Consistent with the last results we saw, the lateral load transfer across both the front and the rear axles is reduced in terms of max load and spread, if only marginally. But that's okay. We've only evaluated damper changes on the vehicle model so far, but we can use these plots to evaluate all sorts of other tuning options going forward. And our main hypothesis that we can improve the roll frequency sweep results was supported from the very first test result that we saw. So that's it for this entry in the devlog. Thank you so much for watching if you've made it this far. This update was kind of an expansion on the first video, but I want to spend time going into the actual vehicle model more in upcoming episodes. So hopefully that'll be just as interesting to you. Um, See you next time, and thank you again for watching.